everyone, and welcome to the topic of analytical techniques. In this topic, there's a range of sections. You need to be aware of significant figures in this topic. They're critically important, making sure that you're consistent with your use throughout. We'll be looking at volumetric analysis, which revolves around titrations. So the equipment we use for titrations includes a pipette, a burette, a volumetric flask. These three pieces of equipment are highly calibrated, which means that they have a very accurate measure, and so we talk about these being very precise pieces of equipment. We are also then going to talk through how we use these pieces of equipment to perform a titration, and in that titration we then calculate very precisely the concentration of an unknown solution, or we use the particular terminology of standardizing that. We then convert that between a series of units, and you need to be familiar with the converting.
Welcome to Analytical Techniques. Analytical Techniques is separated into three components. The first of these components is volumetric analysis, and we're going to take a look at the outcomes relating to that now. So you need to be aware of 5 different standard units. So when we're talking about these units, we're talking about moles per litre, grams per litre, percent weight per volume, parts per million, and parts per billion. So you need to be able to convert between these units. So let's take a look at that in action. So in this example, the concentration of sucrose in the blood was found to be 3.72 times 10 to the minus 3 moles per litre. Firstly, you need to convert this into grams per litre, and then into parts per million, and finally parts per billion. So taking a look at the first conversion, grams per litre. The big difference you'll note here is that we have started with moles, and we want to get to grams. So the moles part is a huge clue. We need to know the molar mass of sucrose, and we can work that out by adding up the number of the mass for C or carbon 12 times, because there's 12 of them, with the mass for hydrogen 22 times, with the mass for oxygen 11 times. And doing that calculation, you'll find out that the molar mass for sucrose is 342.2965. And when we're talking about this number, when we're talking about molar mass, it's grams per mole. So to convert moles per litre into grams per litre, all we need to do is times the moles per litre value with the molar mass value. And that will give us an answer of, so that gives us a final figure of 6.65 grams per litre. And let's just take a look at those units mathematically. So let's take a look at that mathematically. So what we're saying we've got is moles per litre, and we're timesing that by grams per mole. Now, I'm not sure if you remember back to mathematics, but when we're talking about that, the -1 means it's a fraction on the bottom row. So what we actually have is moles per litre times by grams per mole. And because it's times, both of these cancel out. So what we end up left with is grams over litres, which is the same as grams per litre to the -1. Now, for those of you mathematically inclined, it may help to understand how units cancel like this, and you can work out the formulas if you're given the units. So, what about parts per million? Well, when we're talking about parts per million, we're talking about how many bits per million. And if we think about litres, that's grams per litre, That's parts per thousand. So to get to parts per million, we need to divide by another 1,000. So it's kind of like saying, well, we're going to get how many milligrams per litre. So we just need to divide these grams per litre by 1,000. So we'll end up with 6.65 by 10 to the minus 3 ppm. Okay, and the same train of thought for parts per billion, but this time we're interested in micrograms per litre. So we're going to divide by another 1,000, which gives us 6.65 by 10 to the minus 6. And this time we've got parts per billion. Alright, let's take a look at another one. In this example, bottled water is containing dissolved metal ions, fairly standard. An analysis of this shows that we've got 6.2 milligrams per litre of calcium ions present. Convert the concentration in milligrams per litre to molar concentration first up. So let's take a look at what that means. Well, we've got milligrams per litre, so let's get that in grams per litre. So we need to divide that by 1,000. So that's going to give us 6.2 times by 10 to the minus 3 grams per litre. We then need to divide that by the molar mass. So before, when we were converting 2 grams per litre, we times by the molar mass. When we're going away from grams per litre and back to moles per litre, we need to divide it by the molar mass. The molar mass for calcium is 40.08, so we're going to divide by that, and that gives us 1.55 by 10 to the minus 4 moles per litre. So what about percentage weight per volume? Again, we need it in grams per litre, so we've done that up here, we've done that calculation. When we're talking about percentage, we're talking about out of 100. Litres is out of 1,000, so we need 1 decimal place less, and we do that by dividing. So we've got 6.2 times 10 to the minus 3 grams per litre. Instead, we need grams per 100 mils, so we end up with 6.2 times 10 to the minus 4, and then this becomes our percentage weight per volume. Alright, so a bit of a recap on stoichiometric calculations. These are the ones you do when you've done a titration. There's 2 equations that you should be familiar with, and these are ones that you should have memorized and be able to recall them at any time you need them. The first is number of moles equals concentration times volume, and the other one is number of moles equals mass on molar mass. So knowing the formulas is part of it. The other thing that you need to be able to do is identify the mole ratios. So that comes down to knowing if an acid is monoprotic or diprotic. So let's take a look at 2 examples of that. So HCl is a monoprotic acid. That means it can donate 1 proton, and that comes from the H part of the HCl. Sulfuric acid, on the other hand, H2SO4, is a diprotic acid, which means that it can donate 2 protons. This becomes important when neutralization occurs because it may take more base, or will take more base, to neutralize a diprotic acid compared with a monoprotic acid. And being able to use these mole ratios is critical in being able to work out stoichiometric calculations. So let's take a look at some sample calculations. One of the ways that titrations can be used is to determine the concentration of an unknown. So by preparing a standard solution And using the titration process, we can use the concentration of a known solution to find the concentration of an unknown. So it could look a little something like this. We are after the concentration of the hydrochloric acid, knowing that we've got 35 mils of HCl. We also know that there was sodium hydroxide, and that's 14.8 mils. And we know that we've got the concentration of sodium hydroxide of 0.500 moles per litre. So step one here is that we need to write out a reaction equation. So I've got the hydrochloric acid and the sodium hydroxide reacting. Now I've got an acid plus a base, so I know that's going to form a salt and water. One of the clues about this being balanced is that I've got a monoprotic acid, so only one proton can be donated. So having a look through, double checking, yep, my hydrogens on my oxygen are balanced on the left hand side, hydrogen and oxygen balanced on the right hand side. The NaCl has formed, which is my salt. This equation's balanced. I can see that I don't need to have any other numbers in front, so there's no different mole ratio other than 1 to 1. So if I have a look at what that means for my calculations then, it means that the number of moles of NaOH is equal to the number of moles of HCl. I can then find out the number of moles of NaOH that I used in this solution. So let's have a go at doing that. Remember that N equals CV, so I need to times these two together. There's a bit of a catch though, because the volume I've got here is in millilitres and I need that in litres, so it's 0.0148 litres. So if I times that figure by 0.5, I get 0.0074 moles. And as we said that the mole ratio is 1:1, so that means that 0.0074 moles of hydrochloric acid were also used. Now we want to find out the concentration, so we need to rearrange the formula, C equals N on V. And that then means that we need to have the volume also in litres, so 0.035 litres. So 0.0074 divided by 0.035, and that means that we had a concentration of 0.211 moles of hydrochloric acid. Now this makes sense because we can see here that the concentration of the sodium hydroxide was 0.5, which is a fair bit bigger or larger than the concentration of the hydrochloric acid. And we used quite a bit more in volume of the hydrochloric acid compared with the sodium hydroxide. So I'm happy with that. I'll just fix up my units because I haven't written that correctly, so I need to have moles per litre. And I've then found the concentration of the unknown hydrochloric acid. Let's take a look at another one. Here we've got potassium hydroxide reacting with sulfuric acid. And we're going to get a salt and water again. So in this case we're going to get potassium sulfate and water. Now in this case it's not balanced. So I need a 2 out the front here because I needed to have 2 potassiums to balance with the 2 negative of the sulfate ion. And that means that I also need 2 waters. So we can notice here, this is the difference between having a diprotic acid. So let's have a look at what the question's saying. I'm going to start writing my information for the potassium hydroxide. I know that it's going to take 50 mils. And I know the solution of the potassium hydroxide is 0.5 moles per litre. So I've got the volume and the concentration here. I don't have the number of moles, but I can work that out. I also then need to have my information for my sulfuric acid. So let me write that down here. And I know that in this case I am using 125 mils. Just so I don't have to think about it later, I'm going to convert these into litres. So this is 0.050 litres and this is 0.125 litres. Alright, so now comes the tricky bit. I need to be working out my mole ratio. So what I know is that I've actually got twice as many moles of the potassium hydroxide as I do for every sulfuric acid. So if I work out the number of moles here by doing the volume times by the concentration, I'm going to have twice as many moles as I am going to have for the sulfate. So I'm going to write half N here just to remind myself. I'm going to do that calculation now and work out how many moles for the potassium hydroxide. So that gives me 0.025 moles. And remember, I've got twice as much potassium hydroxide, so I need to divide that number by 2 to give me the number of moles of sulfuric acid, which is 0.0125 moles. And now I've got to work out the concentration. I've got N on V, so number of moles divided by the volume, so I'm going to do that now. And that gives me a concentration of 0.1 moles per litre. Hopefully you can see the way now that I've talked myself through working out the mole ratio. I find it much easier to talk myself through how much more of something I have or how much less of something I have than worrying about using any mathematical ratio, because then it makes sense to me. If you want to use it in a different way and use a mathematical ratio, you can do that also.
Rinsing is a very important part of volumetric analysis, and we need to be aware of exactly what to rinse and how. So the general consensus is when rinsing, we are trying to minimize sources of error. We are trying to avoid any additional dilutions or any additional increase in the concentration of the substance that we are using. When using a volumetric flask, we will rinse it with whatever the solvent is that we are using. In most cases, this is going to be distilled water. So now that you have prepared your standard solution, you are ready for pipetting. When we are pipetting, we are using a very accurate a volume of the standard solution to transfer that to a conical flask to be titrated. To transfer that to the conical flask to perform our titration. To do this, we need to ensure that our volumetric pipette is rinsed in an appropriate way. So we need to rinse the volumetric pipette, pour out a small amount of our standard solution, in this case from our volumetric flask, into a beaker. We need to pipette out the small amount of that standard solution. And then we need to remove our bulb filler, and we need to rotate our pipette to ensure that we have good coverage. So we need to ensure that the inside of the pipette has been rotated and covered with our standard solution, making sure that we go past the filling mark. That is a very critical point, that if we do not go past the filling mark, then we are not going to ensure that the entire pipette that we are using has been rinsed correctly. Once we do that, we may choose to rinse it twice depending on how thorough we are choosing to be. We then empty that amount of standard solution out into our waste container, because we do not want to confuse that with our other standard solution and refill. We then replace the bowl back on the pipette into a new clean dry beaker. We pour a small amount of our standard solution from our volumetric flask. From there, we then pipette up to the mark, making sure that the meniscus line meets the line on the pipette, and we then transfer that known amount into our clean dry conical flask. If we do feel like our conical flask needs to be rinsed, we will do that with whatever the solvent was that we filled up in our volumetric flask. In most cases, that will be water. Now that we have a very accurate known amount of standard solution in our conical flask, we are able to carry on with our titration. The amount we have pipetted into our conical flask is known as the aliquot. We are then able to perform a titration into the aliquot and look for a pale colour change, which will indicate the end point of our titration. In addition to our standard solution, we will have something in the burette, and if we have made up a standard solution, we generally want to standardize what's in the burette, which means we want to know the concentration to a very precise amount in the burette. So to do this, we first need to rinse the burette. We will rinse the burette with whatever we are putting in it. To do that, we fill up the burette a little bit. We let it run out of the tap. Once we've run it out of the tap, we want to make sure that we leave the amount in the tap and we don't run the whole solution out. We then fill up the burette a little bit more and we tip the burette, rolling it. The solution has touched and coated the entire area of the burette. We will then put the burette vertical and fill up close to the top. Doesn't need to be to 0 though, but we then need to take a very accurate reading of the burette, making sure we read from 0 being at the top right down to 50 being at the bottom in the burettes that we will be using. Again, we need to make sure that we take into account the meniscus of the line and get at eye level to avoid parallax. The volume of liquid that comes out of the burette is very accurately known, and we need to make sure that we are reading it to 2 decimal places. The volume of liquid that comes out of the burette is known as a titer. So we need to take the initial reading and the final reading, and the volume difference is that titer value. Often when we take the titer value, we're looking for a colour change, and that colour change we will measure firstly a rough titer, and then we will be more precise in the way that we go about it, and we will start to measure closer to the values. When we are doing a titration, we are aiming to get consecutive titers, which means we are aiming to get titer values that are very close together within 0.1 of a mil. This indicates precision in our results. So close titer values indicates precision, which indicates that we have minimized random errors.
Alright, let's have a look at this question. A local town has a lake. It's got 20,000 litres of water in it. And there was found to be some H2SO4 in the lake. So a sample from that lake was taken. We've got 20 mils in that sample, and this was titrated with 15.5 mils of 0.15 mole sodium hydroxide. So something else that you need to know to solve this is you need the equation. So let's have a look at the equation. We've got H2SO4 plus sodium hydroxide goes to form a salt and water. So in this case, the salt's going to be sodium sulfate and water. So because we had 2 hydrogens to the sulfate, we also need 2 nitrogens to the sulfate, which means that we need 2 sodium hydroxides. So 2 sodium hydroxides. And to finish balancing that out, we need to end up with an extra water, so we need 2 water. Alright, so what this actually means, if we're breaking down and thinking about what's going on here, for every hydrogen sulfate, we need 2 sodium hydroxides to neutralise it. This is important for our mole ratio, and we'll come back to that in a minute. Let's start by writing out all of the information we know. So firstly, we know that in the entire lake, so the volume of the lake is 20,000 litres. The next bit of information we know is that 20 mils of H2SO4 and we now need that in litres, so it equals 0.020 litres, was titrated with 15.5 mils of sodium hydroxide. So now we have volume of sodium hydroxide Alright. We also know the concentration of sodium hydroxide. So concentration of sodium hydroxide was alright. So based on this, we can calculate using our formula C equals N on V, so N equals CV. We can calculate the number of moles of sodium hydroxide. So I'm just going to use my calculator to do that. And remember that was 0.15 times by 0.01555. Just give myself a bit more room. So the number of moles of sodium hydroxide equals 0.0023325 moles. I'm not going to round at this point, but I do know at a later stage that that's an incorrect number of significant figures, and I'll have a look at that then. Alright, we need to now look back to our formula and think about what we've done. So we've calculated the number of moles of sodium hydroxide, and we found that that was equal to 0.00233325. Fantastic. Now that is in this bit of information. Now we know that it takes 2 moles of sodium hydroxide for every 1 mole of H2SO4. So we've got twice the number of moles here. So we need to divide this number by 2 to give us the number of moles of hydrogen sulfate. So I'm going to divide that by 2. So it gives me the number of moles of 0.001165. Alright, we need to now look back to our formula and think about what we've done. So we've calculated the number of moles of sodium hydroxide, and we found that that was equal to 0.00233325. Fantastic. Now that is in this bit of information. Now we know that it takes 2 moles of sodium hydroxide for every 1 mole of H2SO4. So we've got twice the number of moles here. So we need to divide this number by 2 to give us the number of moles of hydrogen sulfate. So I'm going to divide that by 2. So it gives me the number of moles of 0.001165. Now the question's not finished, because what it actually asks is how much sodium hydroxide is it going to take to neutralise this? Now I know that the number of moles of H2SO4 in 20 mils was this. I now need to know the number of moles in 20,000 litres. And again, we're not done. So that's the number of moles in the lake. We now need to calculate how much sodium hydroxide we need to neutralise that. So we'll need to have another look at our formula to remind ourselves about the number of moles. So I'm just going to add that now to the list of things I know. Alright. From here, I can work out the concentration of the hydrogen sulfate. And I do that by the number of moles divided by the volume. And that gives me 0.0583125. Now the question's not finished, because what it actually asks is how much sodium hydroxide is it going to take to neutralise this? Now I know that the number of moles of H2SO4 in 20 mils was this. I now need to know the number of moles in 20,000 litres. So have a bit of a think about what I need to times that by. Alright, so hopefully you've had a chance to have a bit of a think about that. And to find that out, we actually need to times by 1,000,000. So we need 0.00116625 multiplied by 1,000,000. And that will give us the number of moles in the lake. So the total number of moles in the lake is 11,662.5 moles. And again, we're not done. So that's the number of moles in the lake. We now need to calculate how much sodium hydroxide we need to neutralise that. So we'll need to have another look at our formula to remind ourselves about the number of moles. Alright, so having a look back at how this relates to our formula. We've said that the number of moles of H2SO4 in the lake is 11,662.5, and we want to know how much sodium hydroxide we need to neutralise it. So having a look, we need twice as many moles of sodium hydroxide to neutralise this. So we're actually going to need 2 times the number of moles of H2SO4. So the number of moles for the lake of sodium hydroxide is 2 times Alright, so we put that into our calculator. And that gives us 23,325 moles. Now the concentration of the sodium hydroxide hasn't changed, so the concentration that we're using is 0.15 moles per litre, and we would remember that our formula is C equals N on V. So we want to find this time how much volume we need. So we're going to need the formula V equals N on C. So the volume of NaOH that we need in the lake is equal to the number of moles, which is that, on the concentration, which is this. So we will need 155,500 litres of sodium hydroxide to neutralise the lake.